Hi, this is the tutorial for the Introduction to QuantLib Part 3. In this tutorial, I will demonstrate how to use the tools from QuantLib, such as statistical tools or optimizer, to solve some finance problem like calculating a portfolio VAR by model building and also by applying extreme value theory. We will follow some examples from the chapter 14 and 15 of John Ho's book, Risk Management and Financial Institutions, to calculate a portfolio VAR using those QuantLib tools and to compare the results calculated from the program against the textbook. In the last tutorial, we have already gone through a model building method to calculate a portfolio VAR. It involves collecting the daily return data in the portfolio, calculating the covariance matrix, calculating the variance of the portfolio return, and finally the portfolio VAR can be obtained. The flow is corresponding to chapter 15, example involving 4 investments. In these sections, the daily returns were collected over 500 days and they can be found here. Using this data, the calculated covariance matrix can be found in the table 15.4. Then the calculated variance of the portfolio returns, and finally the VAR result can be found here. Now let's see how we can implement this approach. First of all, in Visual Studio, create a new project for console application. Select Visual C++, Win32 console applications. Give this project name VAR. And then put this project into our work folder. Click Next, select Empty Projects, then uncheck Security Development's Lifecycle Check. Press Finish. We need to tell the compiler where to find the include path and the library path of QuantLib and Boost library. Select VC++ directories and add the include path and library path there. These paths can be found in your work folder that you have created in the previous tutorial. Next, please add the following flags into the C++ preprocessor setting. After the new empty project is created, let's add a source code into the project. Right-click Source File folder, add a new item, name it var.cpp. The source code editor window is now opened. At the beginning of the source code, we should put the QuantLib header and the directive to disable some warning message. Also, we should put the main functions as the starting point of the code. Next, we need to collect the daily return data to work on this var calculation exercise. We can download the data from the online materials from this book. Then we can convert the daily return data into CSV file. Here is the code to read in the data. We will not go through the code because it is purely implemented by the standard C++ library. The next step is to implement the model building method using QuantLib statistical tools. To calculate the covariance matrix, we use QuantLib sequence statistic class to store the data sequence, and then we use a vector to pass the data entries to the sequence. and then we implement a for loop to collect the data entries. Which are the daily returns from the 4 index funds, and then we put them into the data sequence using the sequence statistic add function. And after collecting the data, the covariance matrix can be calculated using sequence statistic covariance function. After we obtain the covariance matrix, next we could use QuantLib matrix tools to calculate the variance of the portfolio return. The alpha matrix here is referring to how much we have invested into each index fund. After we obtained the variance of the portfolio return, next we could use math tools from the Boost library to obtain the standard normal distributions z-score at the certain confidence levels, like 99%. And then finally the VAR of the portfolio can be calculated. Okay, let's build and execute this code to see what happened. As you can see, the result computed by the program is slightly larger than the one shown in the textbook. The reason is because QuantLib used the data to calculate the sample covariance matrix, while the textbook used the data to calculate the population covariance matrix. To align the result, we can scale the QuantLib covariance matrix by n-1 over n. and then we can calculate the variance and var of the portfolio return again. This time, the result computed by the program is exactly matched with the textbook. That's great. We have completed a simple exercise to calculate portfolio VAR by a simple model building approach. Next, let's calculate the portfolio VAR again, but this time we use the exponential weight moving average method to update the covariance matrix so that more weighting will be given to more recent data. The idea is like this. We start from the covariance matrix that we have calculated previously. Then, for each historical data, we update the covariance matrix incrementally by a factor of 1 minus lambda. While we can implement this EWMA method inside the body of the model building function, alternatively, we can create a derived class from the sequence statistic class, and then we add a new function to implement this EWMA method there. In that case, we may reuse this derived class if we need to use it in the future. So here is the code. The derived class is created from sequence statistic class, and then a new function is created to implement the EWMA method and return the updated covariance matrix. Here is the body of the EWMA method. Firstly, we reconstruct the daily return vector. Then, using the daily return vector, the covariance matrix would be updated incrementally by a factor of 1 minus lambda each time. After the updated covariance matrix is obtained, we can calculate the variance and var of the portfolio returns as before. Here is the result from the textbook, and here is the result from the program. And we can see that the result is matched with each other. Now, we have gone through how to use QuantLib statistical tools to implement the var calculation using model building methods. We have done the basic equal weighting method and then the EWMA method. Next, let's see how to use QuantLib optimizer tools to implement the var calculation by applying the extreme value theory. The extreme value theory focuses on the tail of the portfolio loss. It suggests that we can model the excess loss by the generalized Pareto distribution. The generalized Pareto distribution has two parameters. Parameter C represents the shape. Parameters beta represent the scale. Here is the code to reconstruct the excess loss data for the extreme value theory calculation. We will set the loss threshold U to be 160, which is according to the textbook. we should find the parameters C and beta such that the resulted generalized Pareto distribution can best fit the excess loss data distribution. To do so, we should formulate the likelihood function first. For the generalized Pareto distribution, the likelihood function is like this. For each of the excess loss data Y, it is calculated by the historical portfolio loss data V minus the threshold loss point U that representing the tail. Here is how we implement the likelihood function into the program. Notice that the likelihood function is negated. I will explain the reason shortly. After formulating the likelihood functions, we can then use the maximum likelihood estimation method to find the parameters that can best fit the historical data. The objective of the maximum likelihood estimation is to search the parameters C and beta such that the likelihood function result is maximized. We may implement the maximum likelihood estimation method by our own program code to explore all possible C and beta iteratively. However, it may take us time for programming and debugging the code. On the other hand, we may use the QuantLib optimizer tools to achieve this purpose. The optimizer tools in QuantLib will minimize the cost functions that we have defined, and that's why we add a negative sign to the likelihood functions that we have implemented previously. In that case, minimizing the cost functions will be equivalent to maximizing the likelihood function. After we obtain the parameters C and beta by the optimizer, we have done to model the tail of the portfolio return. Lastly, we can calculate the var of the portfolio return by this formula. And here is the code to implement the var formula. Let's build and run the code and compare the result with the textbook. As you can see, the calculated C is 0.436 and beta is 32.53. The parameters and the var results match with the result in the textbook. That's all. I hope you enjoyed the tutorial and get some understanding on how to use QuantLib. In the next tutorial, I will demonstrate how to use QuantLib analytical method and Monte Carlo method to price an option. See you next time.